Okay.
All right, everybody, welcome to our 14th Geometry Topology Summer School, and our first speaker is Federico Trinca from University College London. He's gonna talk about calibrated geometry in non-compact complete manifolds of exceptional holonomy.
Thank you very much for the introduction, and thank you very much for the invitation. So thank you. I'm going to talk about this very I think interesting topic in geometry, which is calibrated geometry in non-compact manifolds of exceptional holonomy. So this is going to be divided into 4 courses. 2 are going to be more introductory, and 2 are going to be more research-based. So in this first talk, I'm going to just set the foundation of calibrated geometry and manifolds of exceptional holonomy. So if you don't know what any of these words means, that's fine for now. I'm going to first introduce what is a Riemannian holonomy in the first place, and then I will talk a little bit about calibrated geometry, and finally the 2 exceptional holonomy groups that are G2 and spin 7. So if time permits, I will just go over some group actions and manifolds at the end of this lecture. Otherwise, I will have to cut some time here and there to cover these things, because I don't think they're common knowledge and are going to be very useful for the fourth lecture. So please feel free to interrupt me at any point. I'm going to try to be as self-contained as possible, but please interrupt me. Okay, so let me start by telling you a bit about Riemannian holonomy. So the setup that I'm going to use is a Riemannian manifold, MG, and I'm going to pick 2 points, PQ, that are here. So I'm representing my Riemannian manifold as a potato. Can you see the screen? Is it okay? Can you see? Okay.
Perfect.
And what we need first is, I'm going to recall a very basic Riemannian geometric object, which is parallel transport. So we have gamma, a path from my manifold into a, from 0, 1 into my manifold, which is a piecewise smooth map. And I assume that gamma of 0 is equal to P and gamma of 1 is equal to Q. So it looks like this, the support. So the idea is that for every vector V in TPM, which I'm representing like this, so this is my V, then there exists a unique big V, which is a vector field along gamma, such that V of P is equal to V, and so V of 0, sorry, is equal to V, and it is also parallel, so gamma dot of V is identically equal to 0. And this is just ODE theory. So given such a map, such a vector field, we're essentially constructing something that looks like this in my manifold, and V is equal to V of 1. So from this very simple and basic definition, I can, this construction, I can define what is called the parallel transport map. So for every gamma as above, I have a parallel transport map and the parallel transport map along gamma is the linear map, which is defined in the obvious way. So P gamma is a map from TPM into TQM, that to a vector V, we associate the big vector R1, which is V is the vector field that I constructed above. So you can immediately check that existence and uniqueness of such a vector field gives you a linear map, and so we have defined something which makes sense. Okay. Now, such a parallel transport map has many interesting properties. First of all, the inverse orientation properties. I mean, it's not standard definition, standard nomenclature, but so if I define gamma to the -1 to be the path which to t is mapped to gamma of -t, so I'm just going through my path with the opposite orientation. So instead of connecting P to Q, I'm connecting Q to P. Then what you know is that P of gamma to the -1 is equal to P gamma of the -1. So if I go along the path in one direction, I get a map, and if I go along the other direction, I get the inverse. The second property that I will use is that if I define gamma star beta as the concatenation map, so this is something you probably have seen in your topology class, but gamma star beta of t is just defined as gamma of 2t if t is in 0, 1/2, and gamma of 2t, 1 minus 2t if t is in 1/2, 1, and these are gamma and beta chosen suitably, then I can define P of gamma star beta as the parallel transfer map of this concatenation. And what it turns out to be true is that this is equal to the composition of gamma and beta. And finally, if I see P gamma as a map from my tangent space with a metric into another tangent space with another metric, then this is an orientation preserving map. And it also preserves the inner product, so it's an isometry. The proof is extremely simple, but you can see it in this way. So for every V in TPM, we have V, the parallel transport vector field constructed before. And from this, we can define a V prime of T, which prime here is no derivative at all. It's just, let me call it tilde then. The tilde of T defined as V of minus T. This is again a parallel vector field, and so it tells us that P gamma and P gamma to the -1 are the same map. And we conclude. I mean, this is just obvious. You just have to think about it for 1 second. And similarly, we can do one. Similarly to one, we can do two. So we just define the vector field to be the concatenation of the two vector fields, and you get the conclusion. The one that is just slightly less trivial is the third one. So you can prove it by taking two vector fields of TPM and V and W be the parallel transport vector fields. And if you compute now the derivative of this inner product, then by metric compatibility, you know that V is equal to G of T nabla gamma dot V W plus G of V nabla gamma dot W. And by definition, this is zero, so this is zero. And so this implies that VW, which is equal to big V in 0, big W in 0, is equal to big V at 1, W at 1, but V is precisely P gamma of V and P gamma of W. And so this proves that it's an isometry, and similarly, you can prove that it is the same invariantation. Okay. Now, given all these properties of this parallel transport map, we can define the Riemannian holonomy group. And the Riemannian holonomy group is just, as you could imagine, is defined as the group given by P gamma, where P gamma is an element of SO TPM. And this was proven by this set of propositions here. And gamma is a loop at P. So essentially, we are taking a point and we're looking at every loop based on that point and doing parallel transport. And this turns out to be a subgroup of SOTPM. And this we've proven by these two properties here. And what it is also true is that the holonomy group is a Lie subgroup of SOTPM. And its Lie algebra, it will be denoted by SO-TPM and, whole TPM, and is called the holonomy algebra. So the proof of this definition proposition, so the proposition is in here, is this set, this is the proposition, because a priori it's just a subgroup of SOTPM and not a Lie subgroup. In order to prove that it is a subgroup, what you need is a Yamabe theorem, a theorem of Yamabe, which says that it is enough to show that the holonomy group is likewise connected. And if we manage to do this, then it says that each likewise connected subgroup of a Lie group needs to be a Lie subgroup. And so we would be done. And in order to show this, we have assumed that the first fundamental group is 0. So every loop based at T is going to be contractible. So it means that we have a path of loops. If this is my gamma, I have a path of loop gamma S, which is going to contract to the constant path. And so each loop can be connected to the constant path, and we are likewise connected. So this is more of a sketch of the proof, I guess, than a complete proof. Done. Okay, any question on the definition of the holonomy group? Okay, if not, we can move on. And so we have defined this subgroup of SOTPM for every point. How are all the other points in all the holonomy groups of these Riemannian manifolds for every point related to each other? And can I give a definition of a subgroup which is independent of the base point P? So what I claim now is that the holonomy group of G, which is contained in SOTPM, can be regarded as a subgroup of SON, so as a subgroup or independent of TPM, and this can be done up to conjugations. And the reason is in this picture here. So if you look at my holonomy group as Q, which is another point, then I can connect it through P and through gamma to P. And with this connection, I have that the holonomy at Q is equal to P gamma. composed with holonomy group at G composed with P gamma to the -1. So essentially, I go along gamma, I take the holonomy group and I go back to my original point. And I'm just doing a conjugation, and so this is well-defined after conjugation. In reality, the term holonomy group is hence misleading, because usually we will refer to the subgroup as a subgroup of SON. What it would be more correct to say is to call these, so this is a misleading name, because it's defined after conjugation, and so it would be better to call it holonomy representation, but, well, we're stuck with this name for now. Okay, so now I told you in this 20 minutes, first 20 minutes, that given a Riemannian manifold, I can associate a group, which is this holonomy group, which is independent of a point up to conjugation. So I've given you a way to associate to any manifold, any Riemannian manifold, a group, which is very good. Now, a natural question is which subgroups of SON can appear as the Riemannian holonomy of some Riemannian manifold. So what is the image of this map from Riemannian manifolds to subgroups of SON? And the answer was given by Berger in 1955. It is the final version of many years of study of holonomy. But what Berger proven was that if my Riemannian manifold is simply connected, irreducible, and not symmetric, and I will come back to these two in a second, but then the only possibilities that I have are the following. So I can either be with holonomy SON, and this is usually called the generic case, because I don't have any restriction on the holonomy. Then I can have holonomy that is where UM needs to be even. So my manifold needs to be even dimensional, and this corresponds to the Kähler case. So it corresponds to Kähler geometry. So if I have holonomy equal to I'm a Kähler manifold. Then I also have SUM, which corresponds to the Calabi-Yau case. And if I have holonomy, which is SPM, then I am hyperkähler. And if I have holonomy equal to SPM times SP1, it is usually called quaternion Kähler. And finally, I have the groups G2 and 7, which are purely only in dimension 7 and 8, and these are called the exceptional holonomy groups. And you can see that these are exceptional in the sense that they only appear in two precise dimensions and don't appear in a one parameter family. So the intuition behind these groups is essentially coming from division algebras, but I'm not going to go there. But these groups, you can see, are related to the complex numbers. These are related to the quaternions, and these two are related to the octonions. And it's going to be just slightly more clear at the end of this lecture why. But I have told you that we're imposing two conditions that are irreducibility and non-symmetric. So let me elaborate on that. So irreducible means that we are not locally the product of two metrics. So we're not locally M1 times M2 with a product metric. So this implies in fact, the reason why we're excluding locally irreducible is because if we're in this situation, then the holonomy group splits as a product. And so we can kind of consider the Berger groups as the building blocks of cross products of this kind of object. And finally, symmetric spaces have a lot of structure and were completely studied using algebra. So are less interesting in that sense. Okay. Any question on Berger's theorem? Okay.
The Yamabe you mentioned is the same Yamabe as Yamabe problem, right? In the previous slide.
I mentioned Yamabe's theorem. So it's a theorem of Yamabe that says if you are a arcwise connected subgroup of a Lie group, then you're automatically a Lie subgroup. Okay. That's the theorem. Yeah. No, it's not related to the Yamabe problem of
different guys then.
What?
They're different guys from each other.
I'm not sure. I think I might do this. I think they could be the same person.
Okay,
but
so first time I recognize this result, but yeah, that's why I asked. Okay.
Right, thank you. Okay, so we have this good answer to the first question, which is what is the image of this correspondence of this? So the second question that can arise is, so what is reduced holonomy telling us about the geometry of M? So I told you, I can only have these certain subgroups of SOM, but what is really telling me? So the first geometric consequence of having reduced holonomy is a condition on the curvature, and this is due to Ambrose and Singer in 1953. So what they proven was that for every point in M, the Riemann tensor, which is an element at one point of TPM, lambda2 TPM tensor, the endomorphism of TPM. What they proven was that in reality, this is in lambda2 TPM tensor the holonomy algebra of G, which is a subalgebra of the endomorphism of TPM. And the second consequence is essentially a reverse of this statement. So for every point in M, the holonomy algebra of a holonomy group is spanned by the following, which is P gamma to the -1 R Q P wedge W P gamma for every Q in M is the Riemann tensor, and for every two vector fields VW in TQM, and for every gamma connecting P and Q. So essentially, it's telling us that the Riemann curvature tensor is very strictly related to the holonomy of the holonomy group. So these I'm not really going into many more details about the Ambrose-Singer theorem, but what I will need and I will talk about extensively is the second consequence, which is about constant tensor. It is called the holonomy principle. So the holonomy principle tells us essentially that we can characterize which are the constant tensors of a manifold with reduced holonomy. So S, a tensor, which I'm going to denote by TR SM, so is a tensor of type RS, is such that nabla of S is identically equal to 0. So if I have a constant tensor, then for every point of M, SP, which is an element of TRSM P, this is invariant under the holonomy representation. And on the other end, if I have S, an element of TRSM at P, which is such that it's invariant under the holonomy action. So is invariant under the holonomy of G, then there exists a unique tensor which is parallel, and such that this tensor at P is equal to S. So essentially, if I'm invariant under holonomy, I can use parallel transport to define a global tensor. And the proof of this fact is quite easy. I'm going to sketch a proof. So for every point in M, I'll show you this the first statement. For every point in M and for every gamma loop around P, and we know that S along gamma is parallel. And this is because it's parallel in general, and so if I restrict it to the curve, it's going to be also parallel there. So this means that P gamma of SP is equal to S of gamma of 1, which is equal to SP. And so this implies that S is invariant under the holonomy action. And this proves the first part of the statement. So on the other end, if I take 1 point Q in M, and so okay, in the second part of this theorem, what I want is to construct a tensor. And so what I do is I for every Q in M, I pick gamma, a path connecting P and Q, and I define S at Q by the parallel transport along gamma of my vector field S, of my tensor S. So what I need to show now it's that this needs to be well defined, but this is obvious because of the invariance under the holonomy action, the holonomy representation. Because if I go one way and I go back in another path, then I need to get something which is invariant, and S is invariant under it, and I get that SQ is equal to P gamma of S is well defined. Sorry. Okay. So the last thing about holonomy that I'm going to say is that really the holonomy principle, it's really telling us which is the correct subgroup of SON that we have. Indeed, GP, which is a subgroup of SOTPM fixing all parallel SP for every S. So, sorry. The GP is the subgroup of SOTPM that preserves S at P for every S parallel, then what you can show is that GP is equal to the holonomy group. There is not really a corollary because it's not really obvious, but let's take it as a fact. Okay, any question on the holonomy group? Okay, so I have still a lot to cover. So let's move on to the calibrated geometry. So we have just seen using the holonomy principle that if my holonomy group is strictly contained in S1, then I can find constant tensors, and in particular constant K-forms. And these constant K-forms then are going to be closed in particular. And after rescaling, I can choose them so that they are with commas less or equal than 1, which is this condition here. So we kind of see why Riemannian holonomy reduction. So holonomy reduction implies existence of certain objects that I'm going to define now. So this was a motivation, essentially, of why we can be interested in calibrated geometry. So first, let me give you the definition. So given a Riemannian manifold MNG and alpha a K form, so alpha is a calibration if the two conditions for the equals are true. So the alpha is equal to 0 and alpha E1, EK are less or equal than 1 for every E1, EK unit vectors. Dual to a K form, we can define calibrated submanifold. So if sigma K it's a manifold of a man, it is said to be a calibrated submanifold. If alpha, the K form, the calibration restricted to sigma, gives you precisely the volume form of sigma. Okay, so I given you, I told you I have Riemannian holonomy reduction, and this implies in particular that I have closed K forms and K forms with commas less or equal than 1 in a fairly natural way. And I told you that associated to them we can define certain submanifolds. But why would we be interested in such a submanifold? And the response is coming from this fundamental lemma of calibrated geometry, which says that if sigma K is compact and calibrated, a manifold, then it is homologically volume minimizing. And homologically volume minimizing submanifolds are in particular example of minimal submanifold and stable minimal submanifolds. And you will hear more about these kind of things by in the next lecture by Justin. Okay, now I will give you a very brief proof of this fundamental lemma of calibrated geometry. So if I have sigma prime, which is homologous to sigma, then I can compute the volume of sigma, and this is equal to the integral over sigma of the volume form of sigma. But now, by the condition here, we know that this is equal to the integral over sigma of alpha. And now, once again, by the fact that sigma is homologous to sigma prime and the alpha is equal to 0, this is equal to the integral of sigma prime of alpha. And by the Comas condition, which is this condition here, implies that this is less or equal than the integral over sigma prime of the volume form of sigma prime, which is just the volume of sigma prime. In particular, this compact condition can be weakened, and you can see that this is true if sigma is non-compact. And we don't know that it's homologically volume minimizing, but it is only locally volume minimizing. Okay. Any questions on this lemma and the definition of calibrated manifolds? Okay, so calibrated geometry is so we begin with the definition of calibrated manifolds and calibrated and calibrations. Now, I told you at the very beginning, probably with a bit of confusion in it, that the reduced holonomy is giving us naturally calibrations. And here are the examples that are coming from Riemannian holonomy. So if my holonomy is equal to the unitary group, so if I'm a Kähler manifold, then I automatically have complex manifolds that are calibrated, and this is a very classical result, which is due to Rittinger's inequality and Federer. Then we also have that if my holonomy is equal to SUM, so I'm a Calabi-Yau manifold, complex manifolds and special Lagrangians are examples of calibrated manifolds. And if my holonomy is equal to SPM, so if I'm a hyperkähler, then I have an S2 family of complex structures there, and so I have an S2 family of possible complex manifolds. Finally, I have the two examples that I'm going to talk about later in this mini course, which are associative and co-associative and Cayley's. So before I turn into G2 and spin 7 geometry, let me observe that if sigma k is a the manifold of Mn G alpha, and it is calibrated by alpha, then Tp sigma k, so the tangent space of sigma, seen as a manifold of TPM with the induced metric and the induced K form, then this is alpha P calibrated. And in particular, what this is telling us is that it is crucial to understand calibrated cones and planes in Rn. And there are indeed many results and interesting papers on this topic. For instance, Jason Lotte, Joyce, and many others. Okay. Let me now turn my attention to G2 geometry, unless there are other questions about calibrated manifolds in general. Okay. So I told you, let me recap what I told you so far. I told you I given any Riemannian manifold, and I can associate a Lie subgroup of SON, and these can only be one of a certain list, which is Berger's list. And in this Berger's list, there are two elements that are exceptional, that are coming only in dimension 7 and 8, and are G2 and spin 7. So I will now start talking a little bit about G2 geometry, and in order to do so, what we need to address is what is G2 in the first place. So what is this subgroup of SO7? So the definition of the subgroup, at least the one that I've given, is the following. So G2 is the subgroup of SO7 which preserves the free form, which is this phi0 here, and this free form, which is called associative free form, has the following form. So it's dx1 wedge dx2 wedge dx3 plus dx1 wedge dx4 wedge dx5 plus minus blah 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 blah. Okay, this is not a very nice form. You can already tell. However, what it is true is that it doesn't, since A is an element in G2, preserves also the inner product of R7 and the orientation of R7, then what it is also true is that A preserves the Hodge stars, and so what we know is that A star phi naught, of star phi naught, is equal to star phi naught. So we're not only preserving this hideous free form, we are also preserving another pretty ugly form, which is this one. Okay, I'm sure I haven't convinced you. I've convinced you that these 3 and 4 forms are quite bad, but now I will give you another couple of characterizations that are hopefully going to give you a better intuition of what is going on. So the first one is phi naught induces a cross product on R7. So if you're familiar with cross products, this is going to come as a surprise, I guess. But as in R3, if you're given 2 vectors, you can associate the third one, which is orthogonal to the plane spanned by the first 2. The same holds true in R7 with the cross product induced by this phi naught. And this is given in the following way. So we have R7 times R7 going into R7, such that to any 2 vectors, v and w, we associate v cross w, which is defined as v0 of u v, and v is a 1 form, so we have to raise the indices and get a 1 vector. So this is a cross product, which means that it satisfies these 2 properties. So we have that u cross v, so given 2 vectors, the third one is orthogonal to the first 2, and this is the condition. And the second condition is coming from the fact that the cross product preserves the length. So if I take 2 orthonormal vectors, then the third one is going to be unit. So in order to prove this first condition here, well, all you have to do is really to look at the definition, and since phi0 is alternating, then this is obvious. And the second one, it is enough to show it for UV orthonormal. And at this point, you can convince yourself looking at the formula for phi naught. Okay. So another consequence of another fact about G2 geometry and this free and fold form is that V naught actually determines across the Riemannian matrix GR7, and this is given by the formula U IU phi wedge IV phi wedge phi. So this is a two form and a three form. So 2 plus 2 plus 3 is 7. And so here we get -6, the inner product of U and V and the volume form of R7. And this also for every UV in R7. So in particular, you could also define this G2 here as the A in GL7 such that A star phi naught equal to phi naught and A star of the volume form equal to a volume form. Okay. So the last fact is that phi naught and star phi naught are actually calibrations on R7. And this is once again obvious because they are parallel and so close, and by inspection they have co-mass less or equal than 1. So the final way to interpret this very hideous formula is by looking at G2 as the automorphism group of the octonion, or by splitting R7 as R3 plus R4, then phi naught becomes the volume form of R3 plus sum over I EX phi wedge omega I, where omega I are the anti-self dual two forms on R4. And this is just by inspection again. The final piece of linear algebra that I need, and hopefully it's not going to be too overwhelming, but if free plane in my R7 is going to be calibrated by phi naught, and it's going to be called physio calibrated or associative, if and only if it's orthogonal, it's calibrated by star phi naught, or equivalently, if and only if it preserves the cross product. And if I'm in the cross-associative case, then the cross product is mapped into orthogonal. So if I take two vectors that are cross-associative, the cross product is going to be in the associative plane. Then finally, if I take two mixed term, then I get something in the cross-associative plane. And this can also be characterized by looking at the free and the fold form, and this is the condition that you get. So this condition is going to be quite useful later in the research lectures. Okay, I am afraid that I'm going to go a bit longer than expected, but so now I've dealt with the linear algebra part of G2 geometry. I will now have a 7-dimensional Riemannian manifold, and I say that this is a G2 manifold if and only if its holonomy group is contained in G2, and it has full holonomy if the holonomy group is equal to G2. This condition can be characterized by saying that M7 is a G2 manifold if and only if we have a free form phi which is parallel, and it turns out that it is equivalent to say that d phi is equal to 0 and d of star phi is also equal to 0, so that phi is closed and co-closed. And second, that for every point in M, we have a linear map from TPM into R7, an isomorphism linear such that TP, so the free-form phi defined here at the point P, is equal to EP star of phi 0. So if I can identify the tangent space with my linear model that I told you before, and phi is called the G2 structure. So the proof is a consequence of the holonomy principle, and plus the fact that G is determined by phi, and this was done in the linear algebra part before. Okay, another interesting fact about G2 manifolds that could be of interest for some of you is that G2 manifolds are in particular Ricci flat. No, however, I don't have really the time to comment more on that, but we are interested in submanifolds, and I finally can give you the definition of associatives and co-associative submanifolds. So a three-dimensional submanifold M7 is associative if it is calibrated by phi, and a four-dimensional submanifold of M7 is co-associative if it is calibrated by star phi. And in particular, what we can see by this correspondence between the linear model and the tangent space is that sigma 3 is associative if and only if for every point P in M, IP of TP sigma is P0 calibrated, and the same for the co-associative. Of course, IP TP sigma is not going to be P0 calibrated by star P0 calibrated. So hopefully all the names now make sense. So in particular, another consequence of this fact is that this lemma, this proposition above, holds true for associative and co-associative. So proposition above is okay, is true in this setting as well. So the last piece of G2 geometry that I will be needing in the next three lectures is that is the local existence and uniqueness theorem. So if I have a two-dimensional submanifold of M7, which is real analytic, then there exists a unique local associative such that, let's call it sigma 3, such that N2 is contained in sigma 3. And N3 in M7, again, real analytic. Now it cannot be generic because I have this condition here, which needs to be true for my three-dimensional submanifold. So N3 real analytic such that phi restricted to N3 identically equal to 0, then there exists a unique local co-associative L4 such that N3 is contained into L4. Okay, sorry, this was a lot of information. Are there any questions about associatives and co-associatives? I know I was very quick, but these are. If you want to know more about the linear algebra of G2 geometry, there are good notes by Valpusky or Harvey Lawson, and I think also Spiro has some notes. Spiro Karagiannis. Okay, if there are no questions on G2, let's just catch something about spin 7 as well. So once again, we need a linear model and define what is spin 7. So for me, the exceptional holonomy group spin 7 is defined as the subgroup of SO8, which preserves a full form phi naught, and such a full form is so this phi naught here is it can be written under the splitting of R8 as two copies of R4 as the volume form of the first copy of R4, the volume form of the second copy of R4 plus omega I with zeta I, and omega I and zeta I are the anti-self-dual two forms of the first R4 and of the second one. So let me recall that on R4 we have the x0 by dx1 minus dx2 by dx3, dx0 dx2 minus dx3 wedge dx1, and dx0 dx3 minus dx1 wedge dx2. So these are the kind of forms that I'm talking about here. Okay, I still have some nice property, linear algebra properties of phi naught and spin 7. So the Hodge star of phi naught is equal to phi naught. Also, phi naught induces a triple cross product. And this is exactly defined in the same way. So a triple cross product is just given by a map satisfying these two conditions. So U times phi times W in a product with U is equal to 0, and this is also equal to U times phi times W V and U times phi times W W. So if I give you three vectors, then I teach you a fourth one, which is orthogonal to the span of the first three. And finally, I have that U times V times W is equal to the volume of the plane spanned by UVW of a parallelogram. Okay, then phi 0 uniquely determines GR8, and it's a calibration. Similarly to above, I have a nice statement characterizing the calibrated four planes. So F, a four-dimensional plane is calibrated by phi naught. And F perp is calibrated by phi naught as well. And if I am given three vectors, UVW in F, then the triple cross product is preserved by it. The triple cross product is in F. And finally, I have this vanishing condition, which is going to be useful later, but UVWY in F, then the for meta, is going to be equal to 0. So pi 7 of UB wedge phi VWY plus VB, sorry, minus VB wedge phi of UWY plus WB wedge phi of VY minus YB wedge phi of UVW, where pi 7 is the projection into the seventh component I don't want to go into it, but it's just has this explicit formula here. Okay, I'm almost. I just need 3 more minutes, and I need to tell you the same things that I told you about G2 in the spin7 setting. So an 8-dimensional manifold M8G is a spin7 manifold if the holonomy group is contained in spin7 and it has full holonomy if and only if the holonomy group of G is equal to spin7. And finally, this can also be characterized by a parallel fold form. So M8 is a spin7 manifold. If and only if we have a fold form phi, which is parallel. Actually, it is equivalent to say that phi is closed in our case, in this case. And we have at each point of M, there exists a linear isomorphism from TPM into R8 linear, such that IP star of phi 0 is equal to phi p. And the proof is, once again, the holonomy principle, plus the fact that phi determines E. As for G2 manifolds, spin7 manifolds are Ricci flat. And a 4-dimensional manifold, submanifold of M8 phi is, which is calibrated by phi, is called a Cayley submanifold. And once again, we have I local existence and uniqueness theorem. So if I have a 3-dimensional manifold of M8, which is Gale analytic, then there exists a unique local 4-dimensional Cayley, which contains M3. And this was proven by Harvey and Lawson using the X-series differential system, EDF. I think I don't have enough time to go through the group actions and manifolds today. So I think I should stop here before I bore you to death. Thank you for your attention.
All right, thank you very much for the nice talk. Any questions? So what's going to be next tomorrow?
Yeah, so tomorrow I will be talking about, the next plan is tomorrow I will be talking about the Brian and Salomon examples and the Foscolo-Haskin Nostrum manifolds. So I told you a bunch of things about G2 and spin7 so far, but I really haven't told you whether manifolds with holonomy G2 or spin7 exist. And this was open until the 90s, essentially, until the mid-80s, actually. And so I felt like it was good to tell you and describe the first G2 manifolds ever found, the first complete ones. And in the third one, I will really go into research papers in the last 10 years, 5 years, and I'll try to describe calibrated submanifolds. In the Brian and Salomon manifolds, and in the first lecture, I will try to describe calibrated manifolds in the Foscolo-Haskell notion manifolds. And yeah, this is the plan. I'll have to talk a bit about group actions and manifolds at some point, but yeah, this is the plan.
All right, thank you very much.